Right. All right. So now we can write that down. Do you guys remember from last week what did I give as an example of a material of low density?
Dry ice.
Oh no.
Was dry ice?
No, material of low density. What did I say? Oh, you're going to make me look bad because I just told Connell 10 minutes ago, I bet if I asked my students what example did I give them of a material with low density. Yeah, a gas of low density.
Oh, helium.
Okay, good, alright. Okay.
Yeah, material.
Material.
When I say material, does that confuse you?
Yeah. Because people think it's...
You only think of solids.
Yeah. Solid, yeah. Or even at least liquid.
But you know this whole chapter is called materials.
Yeah.
Yeah, okay.
So
Copy this graph down.
How much did you bet?
No money.
Okay.
I didn't have enough confidence, perhaps.
Column.
Should we also write gold?
I just, for where, here? No, the Celsius is fine.
The other part doesn't matter too. After it's
Oh,
constant
yeah,
for a
this
while.
one here. Yeah. You can just draw a little upward one here.
There's the steepness.
I think this is the same steepness as the first one, roughly. In other words, Bello, make the middle one the least steep. What you doing, Ming? What have you got on your laptop? Homework for what? You know, homework is to be done at home. Yeah. Even Aoife can tell you this. She knows homework is this. You never do homework in class. Do it at home. Right, have you got that? Yeah? Okay. So, this gives us the idea of what's called latent heat. Does anyone know exactly what latent heat is? That's the second time you've dropped that now, Bello. Come on.
Is the heat required to change a state of matter from
One to another. Nearly. Forgot one thing. Everyone always forgets this.
By 1 mass of the...
Yeah, no, something else more important that everyone forgets. That's it. That's it, yeah. Latent heat is the energy required by a unit mass of material to change its state to a different state without a change in temperature. A lot of students forget to stick that in at the end in the exam. Got that?
Yes.
Okay. Continue. So we have two different names here. We have the latent heat of fusion. Which one is that? Does anyone know which change of state that one is?
Gases.
Yeah, melting. The energy required for melting. And do you know what the other one's called, Abdulali?
Fission.
No. I know why you're thinking that. It's not that. Do you know? Oh. You sure?
Latent heat of wait.
Vaporization.
Vaporization.
That's for boiling. You should write those words down. Fusion and vaporization. Yeah? I know where Dammy's gone. To fix his leap card.
Also lost.
But maybe he lost, yeah. Okay. You've got that? Yeah? Continue?
Yeah.
Okay, good. So, we have a formula for calculating the energy required to change the state of a material. It's actually quite simple. Now, please note, this formula is to change the state only and not to change its temperature. Okay? So if you just want to change the state, how much energy do you need to change the state? It's given by the simple formula ml, where L is the latent heat of the material. And material could mean solid, liquid, or gas.
Fluids.
Continue? Yeah? Okay, so you don't need to write this down. This is obvious, but just to be clear, you all know water will freeze at 0.
Yeah.
Yeah. And water boils at 100. Now, what you can write this down. They usually give it in the exam, so but it's good to write it down. The latent heat of fusion. Now, please note, there is a kilo here. So this is 334 kilojoules per kilogram. So it's 334,000 joules is the energy required. And the latent heat of vaporization is even bigger. It's 2,265 kilojoules per kilogram. It's huge. Did you write those two? Those two numbers are useful to have.
report card will include all the 4 subjects.
Say again?
The report card.
I think it would. I don't know. You'd have to talk to your tutor. Okay, continue. Yeah. Yeah. Okay, next. Note that water could actually be a liquid at 100, and in fact it is a liquid at 100 until it gets enough heat to become steam. Likewise, water could be a liquid at 0 until it loses enough energy to become ice. So just because it's 0 doesn't mean it's ice. Could still be liquid water, okay?
So half for ice, half for water.
Yeah, it could even be in the middle, a transition, yeah. You don't need to write this down, this is just to make it very clear. Imagine a block of ice at -20 which is in a microwave. What will happen? First it will be at -20, then what will happen? It will increase to 0. But it's still ice. It will remain solid for some time, but then it melts. And then it will become liquid water. What temperature? 0. It'll be 0 and then it'll warm up to 100. Is it steam yet? No. It'll be 100 for some time while it boils. Now it'll become steam at temperature of 100. Then what will happen? Yeah, it'll leave the microwave. The steam will start to warm up. Okay, is this okay? Yes? There's nothing to write down here. You know this from life. Okay? Right. Here is a simple calculation I want you to do. I want to know how much energy is required to bring 1 kilogram of ice at 0 to steam at 100. Now, how many formulas do you actually have to use here? 2. First, the ice becomes water, and then what happens? No, not yet. The water then has to heat up to 100. And then steam. Okay, calculate the number here. Which part? Well, give it a try. I'll do it now in a minute. What you have here, son, is you have 1 kilogram, and it's ice, and it's 0 Celsius, and then later it becomes, it's still 1 kilogram, but it becomes steam at 100 Celsius. Then, once it becomes steam at 100 Celsius, you can play video games on it. Right? No? I'm sure you all have Steam accounts at home, right?
Steam.
You know Steam, don't you?
Yeah, no. Steam?
You know Steam? You know Steam.
I know Steam.
Yeah, of course, yeah. Because you're cool, I know. Yeah. What games do you have on Steam? Oh, right, okay. Only Chinese games?
No, Chinese games. Japanese games.
Japanese games, okay.
What's Steam?
Oh, Bella, oh. It's like the best thing ever. Especially when they have sales. Yeah, like I got, like for Christmas I got Portal 2 for like €1 or something. Like $1.99 or something like this, yeah.
What?
Portal 2. It's an old game. It's an old game now. But I've never played it, and everyone always says it's great, so I'm like, I think I'll get it. You played it?
No, but I know.
Yeah. good. I like it. It's like a puzzle game.
Yeah.
It's nice. All right, do you have answers here?
Yeah.
Yeah. So look, the first part is delta Q equals ml, and I'll write L1 for the first one, and then what's next? MC delta theta, and then lastly ml2. So what's the m here? 1. What is the latent heat of fusion?
3.4
Kilo. 100, right?
Yeah.
And then 1, and what's vaporization?
Is this supposed to be 1 or 1,000?
2265000. What's that?
Is it 1 or 1,000
For which?
for the mass?
1 kilogram. What answer did you get here? Pretty big, right? 3017.
1000.
This is it?
Yeah. Okay.
Another 0.
No.
3.02 megajoules. Just to put this, to give this a meaning, this is quite a lot of energy. This would cost, I think, about 20 cents of electricity.
That's a lot.
Well, it is, because it's only a kilogram of ice when you think about it. You know, that's like,
Do you need
yeah, something like this.
Why do you need military?
Yeah, like you wouldn't normally do this. I'm just trying to give you an idea of how much energy this is, you know.
Which is cheaper outside though.
It'd be cheaper to let the ice melt first outside before you heat it up.
The formula I don't understand.
Which part?
ML plus MC theta.
There's 3 stages. Stage 1, it melts. Right? Ice melts, doesn't it? Stage 2, what happens when the ice melts and becomes liquid? You heat it up to 100. And then what happens in the final stage? What happens when the water reaches 100? Come on, tell me about it. What happens? It becomes steam. So there's 3 calculations here to represent the 3 stages of what's happening to the ice. Melts, warms up, boils. Is the confusion that you're adding the 3 together? What's the...
Yeah, like the one in the middle.
Yeah, that's the water going from 0 to 100.
And the first one is...
It melting. And then the last one
The graph,
is boiling.
like the graph.
Yeah. I'm not sure if you have a question or I should continue with the... Yeah? We'll do another example. Now, I have a few more examples, but I have, this last one's a little too hard. I have 2 more examples. Now, I'm going to do the second one only. It's hard, but it has come up in the exam once or twice, and this is the hardest it can be in the exam. So if we can do this one, then we're fine for the exam. Okay? Let's have a look at it together. So you have some ice. The ice is at 0. You mix the ice to your 330 grams. Does anyone know why I picked 330 grams? No?
Yep.
330 is how big a can of Coke is. So it's like the size of a glass. Yeah. Yeah. Yeah, 330. Yeah. Anyways, it's not Coke, it's water. Some ice is mixed to 330 grams of water at 15. The ice and water was mixed until the ice melted. The final temperature was 5 Celsius. Okay, you can all picture this. I have some water. How much water do I have? 330. What temperature?
15.
15. I put some ice in it, I mix it, the ice melts, and now what's the temperature? 5. So the question is, how much ice did I put in? So let's picture this. I have my water, 330 grams at 15 Celsius. Then I have some ice. How much ice? I don't know. We'll say X kilograms at 0 Celsius. I pop it in, mix it all together, and finally it's at 5 Celsius. And remember, I said it's kind of good to picture it in 2 layers. Like the ice is one layer and the water is a different layer. Although in real life we know that they mix together. Okay, so the ice that's now water is at 5, and the water is also at 5. How much ice? X at 5. And how much water? 330 grams at 5. Now before I continue, can you understand the picture of what's happening here or not?
What's that? Isn't it 330 plus X?
Yeah, I've just separated them as two layers. It's kind of convenient to do that mentally, even though we know they're mixed together. Anything else? The water, does it gain or lose energy? The 330 grams. Lose. The ice gains. Guess what? The energy gained by the ice equals energy lost by the water. How much energy was gained by the ice? Well, what happened first to the ice? It melted. How much energy was required to melt the ice? ml. What's the m here? X. And what's the L? 384 or 5? 384?
334.
Oh, 334. Then what happens to the melted ice? Heats up from 0 to 5. What's the formula for that energy? MC delta theta. What's the M? What's the C? 4181. And the delta theta? 0 to 5, so 5. That is the energy gained by the ice. That will equal the energy lost by the water. What is the formula for the energy lost by the water? MC delta theta. What's the M? The C? Yeah. And delta theta? It lose 10. 15 to 5. Yeah, 10. And remember, we like to keep everything positive left and right. Now, a little bit of algebra, and you can discover that this will be the answer.
Yeah.
And that's it. And what is that?
Zero.
1, 1? No. 3887. So 389.
Yeah.
So 38.9 grams of ice.
Yeah.
Now remember I said this is kind of a hard one. But do you understand that this is only hard at one step? Which step? This step. Yeah. This is the hard step. But once you have the picture and solving the equation, that's easy. But a lot of students screw up this step. If a student got this question wrong, they got it wrong because they made a mistake on this step. They'll do something like, they'll say minus 10 here. Or they'll do something like, I don't know, they'll forget about this or something, you know. Why are they equal? Why didn't you ask me just 5 minutes ago when I said they were equal? Yes, you. Yeah. Why are these equal? What did I say? The energy gained by the ice equals the energy lost by the water. Gain, lose. Or maybe I should make it past tense, lost. And then that would be gained. Oh, who cares? Right, okay, can you write that down? Don't. That's outside, don't worry. I will do one more example. I can eat some of the maths time because the next topic's easy.
Okay.
Is this where we see a drill like come through the wall or something?
No, they are moving furniture or something.
Okay. You got that?
Yeah.
Yeah. No, you need a second? Yeah? What you doing, Ming? Are you already doing the homework? I'm going too slow for you, am I? You got your physics results.
No, I know.
You know your physics results.
I know.
It was pretty good, wasn't it?
No, this is
Ah, now Ming. Your physics result was pretty good.
and because they homework, it's not
I think it's pretty good. Should I
No,
embarrass you and tell the class what you got?
no.
I think we already know.
Do you? What do you think she got?
Easter.
Easter.
Maximum Easter. If you know, you know.
Okay. No, I didn't say. No,
Next time. I think you should go next time.
She might have got higher.
Yeah,
Easy.
maximum
She might have got
Easter.
higher.
Maximum
She might have got higher.
100.
Yeah.
Yeah, levels for this physics thing.
Yeah. Physics genius.
Oh, it's homework.
Ah, no, don't be shy.
It's
Ming,
homework,
don't
but
be
still,
shy.
people did
Still.
not get it.
Yes.
So shouldn't your answer be kilograms?
Doesn't matter. That's okay for me. Because it's ice, you know. It seems a bit weird to measure ice in kilograms.
Because you changed the...
No, the answer came out with 0.0389, so I converted it, yeah. Okay. Yeah, this one isn't as hard. So, I'll let you try it first. Look up, you got 200 grams of water, 10 grams of ice. You put them together and you mix them and they're the same temperature, right?
Yeah.
So, what temperature is the ice and the water at if they're the same temperature? Very good. It has to be 0. It's the only possibility. Because imagine the ice and the water weren't at 0. They were at 1. Would you have ice? No. If they were at -1, would you have water? 0 is the only situation where the ice and the water can be at the same temperature. How much energy would you need to bring the total mixture of ice and water to 10 Celsius? Do you understand what I'm asking? How much energy do I need to put into the cup to bring everything to 10? So what needs to happen to the ice? Yeah. Calculate this. I think you can do it. Okie dokie. We getting answers? Calculating now. All right, you should have an answer coming up now. So basically, you need first the whoops, where's this gone now? First, the ice has to melt, doesn't it? How much ice did I say? 10 grams.
Yeah.
So that's ml, and what's that? 334.
Yes.
And then plus the ice has to warm up by 10 degrees, isn't it?
Yeah.
And also, we shouldn't forget that the water it was in has to warm up by 10 degrees as well. How much water did I say there was? 200. 10. So, add those three numbers together and we are done. What is that, Marwan? 1, 2, 1.
2 0. Point 1. No,
1
1 0.
1 2 1 2 0
1, 2, 1.
Number 2
0
0.
Like this.
1 1.
Point 1.
Okay. Yeah. We're okay with this? Yeah. So just for 5 minutes maximum, have a look at the homework questions and then we'll start the maths.